All right, y'all. So these are the readings that are for this last week of like real content. The one that's required that I'd like you to read is the Westfall, Kenny, and Judd. The one that's optional that might help to enhance your understanding is that second one. Jake Westfall in particular is someone who has done a lot of cool stuff with linear max models and writes very clearly. So if you look at some of his past papers, you'll find some good ones. In addition, obviously this is the last week of new content for this course. As with the, as in preparation for the previous in-class exam, I'm going to distribute a review sheet. There's the option to do a collective Google Doc if you like. I'll set that up for you as well. So you should expect things to go similar to how they did at the midpoint, except that, after you do the in-class exam, there's also the final take-home, which does the applied stuff. So quite a bit of testing, but my opinion anyway, it's really good to help reinforce the concepts. So instead of a homework, just like at the midpoint, I'm going to ask you to work on that review sheet, and whatever questions that you have, we can go through on the review day next Monday. So same format as at the midpoint. I've been considering bringing my pet snakes along for the review session. So I know that some people have snake phobias. If that describes you and you'd rather me not do this, I won't be offended. So please come up to me after class or email me or whatever. So this doesn't have to happen. I don't want to put anybody into an uncomfortable situation, but he is a real sweetheart. If you're interested, I'll pass him around. I brought him to a bar, so he's very friendly. And he takes the handling really well. So anyway, unless I hear otherwise, this is my plan. I'll bring him on Monday. But like I said, it doesn't have to happen. So I wanted to just pick up with some loose ends that I didn't cover last week before I move on to new content. I'm going to be continuing on with this running example that I introduced last class. It's an actual paper, so you can go ahead and read the paper if you're interested in this data set, looking at whether people's reports of how they were acting match how observers rated their actions. And before I get to the specifics of the example, this is something that I should have covered back on last Monday, but I didn't explicitly, so I want to be very explicit about this because linear mixed effects models, not only are they a little bit complicated, but part of the complication is that everybody uses different terms for them. So if you see these in papers, these all refer to the same thing. Linear mixed effects models, linear mixed models, hierarchical linear models, mixed effects models, random effects models. All of those are getting at this same concept of having multiple sources of error, being able to account for dependency between certain sets of observations, and going through this process of having a small model for the chunks of your data set and a larger model that that you fit on the chunks, distant sets or slopes or whatever. So it's a very confusing thing if you end up reading about these models in papers or even in textbooks. The terminology is just all over the place. So if you see these terms, it's all referring to the same concept. So one thing that I didn't describe back on the last class, the last two lectures, is, well, so I mentioned how there are multiple ways of calculating p-values, right? And the one that we're using is kind of a Rogers approach. You apply using capital A ANOVA. And I also talked about how this is the fact that there's multiple ways of getting p-values is why when you use Elmer, it doesn't give you the p-values by default. It wants you to choose a method if you want them. So the same principle goes for calculating confidence intervals. And actually, if you use that, there's that function confidence that we've used for our regular linear models. The general linear models, what we've been talking about for most of the rest of the course. If you can use that with linear mixed effects models too, but if you do it, your computer will hang for a bit. You'll get that red message that says computing profile confidence intervals, and you're like, what the heck? Why is this taking a while? Sometimes it can even take like minutes or much longer than minutes. It can take a substantial amount of time if you have a complicated model or a large data set. Well, the reason, there are a couple of reasons for that. One is that the best methods for computing confidence intervals take a while. They just take some computational time. Another reason for that is that unlike with regular linear models, general linear models, the things that we've worked with before, in linear mixed effects models, or at least if you apply this method by default, you get confidence intervals for not just the fixed effects that intercept and neuroticism underscore reported underscore C, but those 4 extra lines are the variance components. The variance in the participant intercepts, those individual intercepts that you get for each participant, the participant slopes, that correlation thing, the correlation between, or covariance is the term I'm using here, between the intercepts and the slopes, that new random effect that I introduced in the last lecture. And for any error that's left over, you get confidence interval for each of those. So there's just more quantities to calculate a confidence intervals for. If you're just interested in the fixed effects, which often will be the case, you can tell this function, hey, I only want you to calculate confidence intervals for the fixed effects. So this is a time-saving device. If you want to do that, you say arm equals data underscore, and then that's it. Data in this case refers to the fixed effects. So little handy time-saving device if you have to do this a bunch of times. If you actually look at the content function that is used for linear mixed effects models, for the Elmer models, so the name of the function is content.mermod. But when you call the function, you only have to say content. So here's the help file for content.mermod. And one thing it's kind of complicated, but one thing that I want to point out to you is this section where it says method equals, and then there are options. So these two, profile and boot, are the best, most accurate way of calculating confidence intervals for linear mixed effects models. And profile is the one that it does by default. So profile is a fine method, but it takes a while to use. Boot is short for bootstrapping. We've seen that term way back when we talked about mediation, I believe. We may have talked about it a couple other times. The way bootstrapping works is that you take a lot of samples of your data set and you use those like 1,000 samples or whatever to create a sampling distribution, you're basically simulating the sampling distribution. Anyway, if you don't remember the details, no worries, but we have seen that method before. And it's perfectly fine for getting confidence intervals for linear mixed effects models. The one that's less good is wall. What a wall confidence interval is it uses that, you might have seen in Elmer output, if you just do summary on an Elmer model, you see reported standard errors. We haven't been t-values, but no p-values. So the walled confidence intervals are what you get if you use those standard errors that are just spit out of the regular Elmer model. It's like basically calculating a, you use those and then you go however far out on the sampling distribution, multiply by that to get your confidence intervals. It's a much faster way of getting confidence intervals, but it's not the best way. So this is fast, but much less accurate. So for most practical purposes, you should use one of these two options. You should not use this option, although it can be okay for constructing graphs if you don't care as much about exact accuracy, which can be fine in many cases. So you can use confidence with the wall confidence interval to create graphs if you want a confidence band. You want the confidence interval at a much different place. That's pretty much the only time I ever find myself using this. If all this doesn't really make sense to you, that's okay. The take home is the default method is fine. It's called a profile confidence interval. And it takes a while to compute. So with complicated models, you might be looking at minutes or even half an hour or longer, depending on how complex your model is. This is generally one of the complications of linear mixed effects models, is figuring out how to do inferences. How to make inferences about population parameters. So a couple notes on graphing. In general, you can use the same principles that you might have used for repeated measures designs with linear mixed effects models, which are basically the same principles as you could use for any other kind of graph. You ought to show both for predictions and some measure of error. And you want to think about showing the things that you want to show and not showing the things that just make things difficult to interpret. These are the same graph principles that we've used for many, many other types of graphs. So this graph right here is a perfectly fine option. It's that spaghetti plot where you're showing the individual lives for each participant. One nice thing about this graph is that it shows the links between different data points. You're respecting the fact that multiple data points came from the same person. What your model actually gives you is predictions for each person. And then maybe a blue line for the fixed effects. This is perfectly fine. It's not the only option that you could use, though. So another thing that you could do, it could be a little bit tough to do the proper programming to get the those individual participants' random effects. If you've in the last in-class exercise, you might have seen that it takes a little bit of finagling. I see some nodding. So for most practical purposes, showing the dots just like you would for a regular graph, that's totally fine. I think if you're able to get the individual participants' prediction lines, that's even better because it shows some information that is not shown here. But I'm kind of thinking about these things, and you don't have to go the extra 5% to get that extra information on the graph. This is like, this gets 95% of the information. The other graph shows a bit of extra information. That extra 5% is not terribly important for most people unless you're obsessive like me. Another thing that you can do is add this confidence band around the prediction line. For this particular data set, we have so much precision that you can hardly see this, this confidence band, but this is what we've seen on other graphs where there's like a transparent envelope that goes around the entire line. So if you're using predict SE, that function that can get you a certain type of standard error for linear mixed effects models, actually it gets you a wall of standard error. That's why it's so fast. You could use predict SE like you would use predict, and it works basically in the same way. If you want to get 95% confidence intervals around this, you'd have to do some programming yourself. So you probably want to use the confidence function a bunch of times at a lot of different points on the prediction line. I'm not going to require you to do that. I'm not going to necessarily show you how to do that, but if you're motivated, that's what you do. You can also, I think you could multiply the standard error by like 1.9, whatever, 1.96, although it's, I'm not sure if it'll match up the entire time, every time, because linear mixed effects models are complicated. Anyway, it doesn't matter. You can show these bands. Predict SE gets you plus or minus 1 standard error. It's a perfectly fine way to go. Yes.
A quick question before we continue. So that last graph, if I were to see that, how would I visually interpret what I'm saying? So it doesn't really make a lot of sense.
So the intercept is way off to the left. That would be the predicted value at 0 on the fixed effects. I think it's going to be 1.1 something. Well, we'll see over the next slide. This line has a slope of, it's a pretty small slope actually. It's a positive one, and it's significantly different from 0. And the slope shows you that for 1 unit increase on people's reported neuroticism, people's coded neuroticism increases by a small amount. Actually, that's going to be on the next slide where we're going to talk about this.
What are these, the dots?
Each of these dots is one observation for one participant. We don't know the links between the dots. Like, we don't know whether this dot goes, whether these two dots, for example, belong to the same person, because I've removed those links. So I think for the best graphs with linear mixed effects models, you find some way to show those links. I think that's a nice bit of information. However, as I was saying, it involves a little bit of extra programming. It's not absolutely required. It's not even necessarily standard when you see people reporting these kinds of models. But I think it's nice. It's my preference to show it. And so it gives you a bit of extra information that is not shown here.
I don't know if we need to know this or not. Is there any interpretation of the clustering of the, what was like more dots in one spot than another?
We can't see that on this graph. We've lost that information. So as I was saying earlier, that's one of the reasons why I like these spaghetti plots, because you get some extra information. So you can see like at, the mean is about 2. You can see the amount of variation in the intercepts. You can see by just how much the individual slopes vary, or how much the individual lines vary with the variation in the slopes. And you can also see, if you care about this, the correlation between intercept and slopes, looking at the direction of the theta. So these are all reasons why I like this kind of graph the best, but it just takes a little bit of extra doing if you want to create this kind of graph. It takes some extra programming for the purposes of, say, the Tate Museum. I'm not going to require you to make this kind, although I think there are some things that make it a little better. Does that make sense?
Mm-hmm.
Okay, let's do a little bit of practice interpreting some of this, the output that we get from Elmer. So if you were to use this 0.08 in a sentence, how might you describe what that slope is telling you?
Can you run this as an outcome again?
We're looking at
Oh, sorry, there it is.
people's reported neuroticism versus their coded neuroticism. So as a reminder, the reported neuroticism is like responses on a questionnaire. Coded neuroticism, you get these audio clips, raters evaluate the audio clips, so we end up with the same scale on each outcome.
So that coefficient could be interpreted as like for every like 1 unit increase from the mean of reported neuroticism, there's a 0.8 unit increase in coded neuroticism.
Absolutely. And you can even think of this as applying to within one participant because of the design of the study and the way we analyze the data. So for a given participant, on average, when they exhibit an increase in their reported neuroticism, their coded neuroticism goes up by an average of 0.08 units. This is kind of interesting to think about in the context of the problem. Remember, this is the same 1 to 5 scales each time. This is positive and significantly different from 0, but coded neuroticism is increasing a tiny amount. So thinking back to the original question in this study, the question is, do people realize, have some sense of how they're acting in the moment? And for this variable anyway, neuroticism, you might have some sense of when they're acting more neurotic, but not a lot. That coefficient is very small, even if it's significantly different from 0. So this is another piece of information I'm going to use in the write-up that I show you on the next slide. But this is right here, the amount of variation in the participant slopes. So if you were to use that number in a sentence, how might you describe what that number is telling you? Yeah.
Is it the increase in the variation of slopes of participants as reporting neuroticism increases?
You can think of it, so the standard deviation, you can think of that as telling you the average deviation from the overall slope for a given participant. So if you choose a given participant at random, will on average still have the fixed effect, the common slope. But if you look at the average deviation from that common slope, that's going to be 0.09, almost 0. It's basically the standard deviation of each participant's slope. You take all the slopes that you get from that first stage of analysis, the individual regressions, and you take the standard deviation of that. That's what that is. So that's telling you, it's very close to 0, right? That's telling you that most participant slopes are very close to the slope of this blue line. They differ a little bit on average. There's some deviation from the slope of that blue line, not a lot.
So how did you say that?
It's the average difference, average absolute difference in the participant slopes from the slope of the blue line.
Is that the standard deviation or is that?
Yeah, that's the standard deviation.
What's the variance?
The standard deviation squared. So those two things, not sure if I've said this explicitly, so I'm glad you asked this. The variance column and the standard deviation column are telling you the same thing, just on a different scale. The variance is the standard deviation squared.
Was the average difference of the slope of a given participant?
From the overall slope.
Overall?
Yes, absolutely.
Is the variable center the reported?
Yes.
So if it wasn't centered, would that change?
Great question. So notice that if I drew a line down the middle, the points at which these gray lines cross the vertical are a bit widely spread. They're a bit less widely spread over here. They're a bit more widely spread over here. So what does that tell you about the variation in the participant intercepts?
Say what was it?
If I draw a vertical line, I'll draw this on board.
It increases, right? As you
Yeah, so if I draw a line down here, there's some amount of variation. If I draw a line over here, points at which each of these individual lines have a different amount of variation and a different amount of variation still.
So if you think you're more neurotic, you maybe be more neurotic, maybe not, just maybe.
Yeah, depending on the level of neuroticism that you're reporting, the variance in people's intercepts. So basically their reports at that point changes. There's more variation at the extremes. Some people kind of get it that they're acting pretty neurotic at that point. Some people really don't. So that tells you something that we covered a little bit on the last lecture, that the variation in participant intercepts is different depending on where you are in the model. But the variation in the slope stays the same. At every point on this neuroticism continuum, if I look at one of these lines, it's going to have the same slope no matter where I am. So centering, getting back to your question, which is a great question, centering will affect the variation in the intercepts, but not the slopes. And then what's the value that controls how much the intercepts change as I change on that neuroticism continuum?
With the optimism?
That'll find the values for us. But there's a piece of output on here that tells us how much the intercepts change as I go a different, yeah.
Is it correlation?
Yes, it's that correlation framework. Great.
So if you center your variables in it, it's going to affect your participant intercepts, but not the slopes.
Yes.
And then the correlation is the relationship between
It's the relationship between distance intercept and slope. Other questions?
So what's the formal interpretation of the random effect? Or is it the same as what you said earlier?
So the line that says intercept, that's a random effect. It's the random intercepts. That tells you the average difference between the overall intercept at a given point of the model, and each participant's intercept. That second line where the red box is, that's another random effect. Those are the random slopes. And where the variance in the random slopes, that standard deviation thing tells you the average difference between the overall slope and a given participant slope. Other questions? So this is a lot of information that we could use to write out this model. And I don't think that there's any one way that's necessarily the one to do. It sort of depends on what you're trying to highlight about the model. I created one write-up that I think is reasonable, but I'm not trying to say that this is the only way to do it. So I'll let you read the whole write-up on your own if you're interested, but in general, I gave some introduction of the context of the problem. We want to know the degree to which people's reports match other people's observations. And one thing that I did is that I state that the relationship is non-zero, but I also explicitly say that it's small. One thing I could have done actually is I could have done a test of equivalence. So that general method that I showed you where you use that LHD command, that actually works with linear mixed effects models too. It's the same procedure. If I have some reason to believe that a slope of below 0.1 is small, I could test the value that I observed against that slope of or the boundaries of what I consider to be a small effect. I didn't do that in this write-up, but that would have been good. One thing that I do report in this write-up is that variation in slopes, the participant slopes, basically to say that most people are close to the common slope. So it's the case that most people have some idea of when they're acting more neurotic, not a lot. Questions?
So you don't mention anything about the change, like are more accurate in the beginning and then they're less accurate? Is there make it higher when reported?
Yeah, I suppose I could have done that. Like I said, there's lots of things that you could do with linear mixed effects models. That could be an interesting thing to do. Yeah, it's a good idea. So just because this is the way I reported it doesn't mean that it's the best way or the only one. But I can see that being quite interesting to point out that the degree to which people disagree from each other is higher at higher levels of reported neuroticism. That seems interesting. Good idea.
Is there a specific way to report something like that?
One thing you could do is you could find the variation in the random intercepts, the participant intercepts at, say, 5 versus 1. Choose 2 points that you care about. And just note that there's a lot more variation at one point than the other. Maybe that's a case where you point out that the correlation parameter is, whatever it was, I think it was like 0.4 or something at the average level of reported neuroticism. Then you report the variance in the intercepts at 2 points. Yeah, it's a good idea. Other questions? Okay, we're going to move on to something new. And before I get into this topic, I want to say up front that it is a little bit complicated. However, I think that it's an issue that comes up a lot in social science data. So what we'll go through today is I'll describe a little bit of why you should care about this, but mostly I'm going to be focused on the mechanics of actually doing it. And I'm not going to give you, I often like to give you not necessarily formal proof, but something close to demonstration of how things work. I'm not going to get into that much stuff here because it's so complicated. I'll try to give you some intuitions as to what's happening. And the readings for this week are for if you want to learn more, and if you want to know some of the technical details, I suppose I could find a reading if any of you are interested, but anyway, I've already provided some extra information if you want to know more about this. So anyway, it's complicated. I'll go into a little bit less depth than I often do. And on Wednesday, I'll talk in more depth about why you ought to care about this and some design choices that you can make to take care of the problems that you introduce. We're going to go back to this problem of looking at rate evaluations. We're actually using the same data set that we've used, I think, on the first day that we started talking about linear mixed effects models. Everybody's evaluating 4 grants. The grants have been previously rated on a 1 to 9 scale. And these ratings are quantitative. So instead of low versus high quality grants, we're looking at grants that were rated a 1, 2, 3, 4, 5, etc. I'm adding in one twist. So obviously, in order to get these grants evaluated, I had to have grants to evaluate, right? I had to have some number of grants, and I had to send them out for review. Well, now my data set will contain information about which grant is which. So did participant 1 evaluate grant 1, grant 2, grant 3, and grant 4, or some other subset of grants? Which grants did they evaluate anyway? So this has always been a feature of this problem, but now I'm just giving you that information in the data set. So let's see what that's like. I've still got a column of participant IDs that tell me which rows belong to which participant. I still got a column of quality ratings, and I've still got a column of new ratings. But I've added one extra column, and that's a column of grant IDs. So that tells me which row belongs to which grant. So what we've been doing this entire time is, I introduced this idea that you can have a little regression equation for each subset defined by a specific person. You apply that regression equation to each subset. That gets you some intercepts and slopes. You can think of that as like creating a new data set that has a smaller number of rows, 50 rows instead of 400 or 200, excuse me. And then you, in that second stage, you take basically like the averages of the intercepts and slopes, or whatever model that you want to fit in the second stage. So that's what we've been doing so far. But consider these rows that belong to the same grant. So if I know that grant ID number 1 was given a good score by participant 1, does that tell me anything about what participant 2 might give that grade? What do you think?
Might just get a good grant, so it's likely to get a high score.
Yeah, it probably does tell me something, right? Likewise, if I have a grant that's a bad grant, Or maybe it was on an unusual topic and reviewers don't know how to evaluate the topic. Well, if person number one, if reviewer number one gave that grant a bad score, probably reviewer number two will, reviewer number three, reviewer number four, and so on. Does this pose any sort of problem for like these models that we've been putting? If knowing something about the score of one chunk of data tells me something about the score of another chunk of data, what problem is that? Yeah.
Does it give us another source of data?
It's another source of possible interdependence between scores. So one of the reasons to use linear mixed effects models in the first place is to account for interdependence. That was one of the reasons that I gave for like doing this with reviewers. Well, now we know a bit of extra information about which rows belong to which grants, the stimuli that the reviewers are exposed to. And that seems like another possible source of interdependence. Grant number one is evaluated especially at the reviewer number one. If I give that grant to other reviewers, chances are they're probably also going to give it bad scores. And vice versa for the good scores. Yeah.
Is this still called linear mixed effects models, or is it like linear mixed?
This is still a linear mixed effects model. Yeah. It's an extra complication in what you can do with linear mixed effects models. And what I've done on this next slide is I've just sorted the data set by grant ID, just so that we can see the chunks of data that belong to a given grant a little bit better. And notice, like, each grant was evaluated a certain number of times. So 5 times and 5 times. And of course, the way we went about, like, solving this problem when we were working with multiple scores given by one reviewer is that we separated the data set into different chunks, right? Well, I'm just going to go through that same process with grant ID. And for now, let's just forget about the fact that the grants were evaluated by separate participants. Let's ignore that feature of the design. Let's just look at the grant part of the design. So now that we have these chunks of information that belong to each grant, I can fit a little model for each of those chunks. I got 40 grants, so that's going to break apart this data set into 40 different chunks, one for each grant. Let me ask you this. Just looking at this small part of the data set, what do you think is going to be the model that I fit on each of these chunks? So I've got 40 chunks, one per grant, and I have to choose a model to fit on each of those different chunks.
Same as before, right?
Well, what was the model? We're focused on the random effects part of the element model. So I have to have an intercept and maybe some slopes. What would be those that intercept? What would be the parts of this model that I fit for each of the chunks of the data set?
It would be the same thing, but you're just going to replace the ID part with grant ID.
Well, let me draw your attention to what's happening with quality. So each grant got one rating. It's either a very high quality grant or moderate quality grants or low quality grants. And quality is not something that changes each time that it's rated. It's the same. How might that affect that model that I fit for each grant?
not taking
Yeah, it looks like quality, because it's not varying within grants. It's something that, like, I can't get an estimate for the slope for grant number one. Quality doesn't change for grant number one, it's the same.
So it's gonna be like participating.
Yeah, it's just going to be a random intercept. Actually, I can scooch that part of the data set up to the next stage, the second stage of the model fit. The general principle here is that if you're thinking about, in general, if you're thinking about what the random effect structure ought to be, you should ask yourself, what varies within unit, within reviewer, or within grants, whatever the unit is, and what does not. Things that vary within unit are things that can go over on the random effects portion of the model. Another way to think about this is that quality is like, this is a property about grants that does not change. So if it's a property about something that's not changing, you can't add it as a parameter to be estimated in the model.
So would that be a fixed effect?
Yes. So we know what the random effects are going to be for this model. We just have a random intercept for grants. One way to talk about that came up in the write-up that I showed you. Sometimes I find it convenient to refer to this as a by grant random intercept. By grant just means that's what I'm using to define my chunks. So that gives me my intercepts. And even though quality did not vary within grant, it still is something that I can use to tell why one grant might have an intercept that's different from another grant. So it's still something that can go in the second part of the model, the second stage of model. I can then sort of use the intercepts that I get for each grant as an outcome and add as an extra parameter quality. Again, quality or quality score might be something that helps me understand why one grant had a higher intercept than another. So far, just to bring us back to the context of the problem, this is the same procedure that we use to understand the linear mixed effects model in the first place. So I've got some source of interdependence, some reason to break apart my data set into separate chunks. I choose a model to fit on the separate chunks. Then I choose a model to fit on the derived information that I get from the chunks. Any questions about that? So all that's to say, I can think about grants in exactly the same way that I think about review. It's another thing that connects separate rows in my data set. Say like 5 rows in my data set each belong to one grant, and I can group my data set into those 40 different chunks by grant. And then fit a model on the chunks, fit a model on pieces of information that I get from the chunks. So here's what that looks like graphically for one particular grant. Some reviewers gave this grant the same score, so that's why some points are a little bit darker than others. And one way to understand what we're doing is that for this particular grant, again, an intercept, that gives me a horizontal line. that's basically the average score for this grant. Or I guess our predicted average for this grant. So here are all the grants in the data sets. The previous score, what I've also called quality, that's something that does not change about a given grant, whether reviewed by multiple reviewers. So that's why all of these points are vertical, because the previous score that the grants got, that's not something that's changing. What I can do is I can draw a horizontal line that represents my prediction for the grant that, or the score that these grants are going to receive. That gives me 40 predictions, one for each grant. And then, this is mislabeled, but what I'm doing is I'm just plotting on the x-axis the quality of the previous score that the grants received. And on the y-axis, I'm plotting the intercepts. So this is the relationship between the previous score and the intercepts, the average score for each grade. That's a linear mixed text model. So, okay, same procedure, but I've picked out a different source of interdependence between multiple rows in this data set. So that tells me that I've got two possible sources of interdependence. One is the reviewers. I had reviewers evaluate multiple grants. And another is the grants themselves. The grants were each reviewed by multiple reviewers. If one reviewer gave a given grant a low score, the other reviewers might also give that grant a low score. And we want to be able to account for these multiple sources of interdependence. There are some specific design reasons that I'll get into more detail on Wednesday. But one of the big picture ideas is that if you don't properly account for these multiple sources of interdependence, you're at much higher risk of saying that there's an effect when there's not, of making a type 1 error or a false positive. So that's one of the big picture ideas. There are other reasons to do it too. But here's one takeaway right now, is that if you're not accounting for these extra sources of independence, the fact that multiple people evaluated one of these signals would be great in this case. That puts you at risk of making a mistake, saying that there's an effect on the result. So here I'm showing you the results when we looked at grants as the source of independence. Here's what you get if you consider participants the source of independence. The graphs look slightly different because in one case, I just had random intercepts. These are the intercepts that I'm showing over here. Here, I also had random slopes. So that's why I've drawn a slope for each reviewer. So the little miniature models that I fit on the chunks of the data set, they're slightly different. Notice though the black lines look fairly similar, they're pretty close together. So in some ways I'm still estimating the same effect, the effect of quality, but I'm doing it in slightly different ways. Here I'm giving you the results of fitting these two different kinds of models. So on one hand, considering grant the source of interdependence, on the other, considering review of the source of interdependence. So one thing we can find out here is that, as we saw on these graphs, we're getting slightly different fixed effects, overall intercepts and overall slopes. They're not exactly the same, but they're similar. So that points at this idea that I'm sort of approaching and estimating the same quantity, but in different ways, and it gives me slightly different conclusions in this case. One thing that's really quite different is what I get for my p-values and f-values. So here, my p-value is really quite low. Here it's still, well, it's about 100-fold higher. So it seems like something's happening to, under the hood, my degrees of freedom and my precision. That's creating a difference when I'm analyzing these two things. So I'll get more into what's causing those differences in the next lecture. For now, I just want you to see that there are some statistical implications for analyzing the results in these two different ways.
Just to be clear, they are still both the same, like just different variables, right? Like you're looking at.
They get you, there are different ways of asking similar questions. Neither of these ways is the best way, actually. For now, I'm just showing you that you can think of multiple sources of interdependence in the same data set. And the question that I'll ask is, well, why not think about both simultaneously? And that's really the best way to approach this specific problem, is you think about the different sources of interdependence in your data set. Often they're there by design, and you account for them in your statistics. So you account for the way you design your study in your statistics. So if you have participants give you multiple responses and multiple stimuli are exposed to multiple participants, well, you have to account for both in your statistics. This is where things get more complicated, because if you're thinking about multiple sources of interdependence, the mathematics for how you get to the estimates of those, the amount of interdependence is a little bit involved. This is where a lot of the complication of the linear mixed effects model comes back in. So this is a place where I'm going to do a little bit of hand waving and not explain exactly how this works. But as you'll see, the way that you actually fit these models using Elmer is actually a fairly simple extension. So the way you get to the estimates is simple, but it has some mathematical complexity. So this is the grant side of things. We're considering grants, again, grants, the model that we're fitting across each of the chunks defined by the grant just has an intercept for each grant. Each grant has basically an average score across reviewers. Once we get those average scores, we have an overall average across all the grants, and we also have an estimate for the slope of quality. So those are those two fixed effects on the second stage of the model that I described just a moment ago. On the participant or reviewer side of things, we have both an intercept for each reviewer, so how harsh or lenient were they in their scores of advance. But we also have quality. So we gave these reviewers grants of varying quality. We can estimate for a given reviewer how responsive their ratings were to quality. So we have a random intercept and a random slope for each reviewer. We're at the second stage of analysis on the reviewer side of things. We have an overall estimate of the average score given by reviewers, the average of the reviewer averages. And we have an average score for the responsiveness of a given reviewer to quality, the average of the slopes for each reviewer. So I'm smushing together these two halves of the model. One thing that's a little odd about this procedure is that I've got multiple estimates for intercepts and slopes that I have to somehow like smush together. And that's one of the pieces of complication where I have to do a little bit of hand waving. There's some math that happens under the hood to reconcile the estimates that I get from these two different portions of interdependence. And how exactly that happens also depends on how the data are structured. That's a point that I'm not going to get into right now. I'll gesture at it on Wednesday. I'll give you some sense of what matters and why, but I'm not going to get into all the details. So for now, just what I want you to know is that there's some procedure to reconcile these estimates together. That happens under the hood. You don't have to do it yourself. So we've got a source of participant interdependence, a source of reviewer interdependence. We've got basically two sets of gradient effects. This is what that might look like graphically. I haven't told you yet how this overall slope is derived, but this is what you get if you fit the model with multiples versus interdependence. And just one thing that I want to point out before moving on is that I advanced the slides. I put a dark red line and a dark blue line for the estimates that you get if you look at each of these sources of interdependence separately. So you fit the model with just reviewers, you fit the model with just grants, and the lines are right on top of each other. They hardly vary at all. That will usually be true. So you're not going to get like wildly different estimates if you did happen to fit the model in this place. At least for the fixed effects. So we're still following this two-stage process. We've got the first stage where we consider our random effects, and the second stage where we consider our fixed effects. What's different here is that we have two sources of random effects. We've got rates, because each grant is probably going to get a similar score across multiple reviewers. And we've got participants, because each reviewer is going to be, either tend to be harsh or lenient, and might have some amount of individual responsiveness to quality.
Sorry, what does V1 mean? And
I often leave these out. This represents the intercept. So I could have just eliminated this one and showing it to show explicitly that we're getting intercepts.
and that one also is, the second one is also intercept.
Correct. One means intercept. So the way this works in Elmer is you just add that extra parenthesis that describes the random effects for a different source. If I want to add random effects for grant, I add parentheses. I say I want the intercepts for grant. I give the thing that tells Elmer how to divide up the chunks of the data set. That's it, that's all you do. So there's obviously some complication that happens mathematically, but when you're working with Elmer, it's really quite simple. You add plus, and then you add the extra random effects that you want to include in the model. So even though there's this like some complexity in how this works, even though like it can be a little bit difficult to understand what it means to have multiple sources of interdependence, when you're actually fitting the model in Elmer, it's really quite simple.
And why wouldn't you have quality with grant ID?
Good question. So I pointed out how quality is not something that changes for a given grant when it's evaluated multiple times. You know, each grant has the same quality score no matter when it's evaluated. It's always, you know, 1 or 2 or 3. So in other words, quality does not vary within grants. No matter how many observations I get for each grant, its quality score is going to be the same. So what tells you what to put in here is what varies within that unit. So for a given reviewer, whenever they saw the grant, that grant had its own quality score. So that's something that did vary within reviewer.
So what's left of that dash, that border line, is what varies within what's on the right?
Exactly. So this stuff, that tells Elmer what's the individual model that I'm fitting these like 50 times, 1 for each participant. Well, for each participant, for each reviewer, I'm getting intercept and a slope for quality. For grants, I'm just getting an intercept. Other questions? I still have this second stage, and that tells Elmer what fixed effects to give me. And the fixed effects part of this model looks the same. So I'm still getting an overall intercept and an overall slope for quality. So for all that's, you know, there's this kind of complicated process happening under the hood. It can be a little bit hard to get your mind around the different sources of interdependence. The way I'm interacting with Elmer has just one extra thing, and that's I'm getting some random effects for the different sources of interdependence. Yeah.
So if you don't include the 1 in that the first random effect parentheses, would you still leave that bar?
So this one, if you only have an intercept, you have to add 1. The only time you can omit the 1 is if you have a slope. And by default, Elmer adds in the intercept for you. It's just a way to eliminate a bit of extra typing.
Yeah, so you don't need it on that fixed effects.
Correct. So for the fixed effect side too, you know, Elmer and LM give you the intercept automatically. You don't have to tell it to give you the intercept. So even if I left it out, we would give it to you. No questions. Here's the statistical model that we fit. So we've got some fixed effects. We've got an intercept and a slope. We've got one source of random effect, which is great. We've got a second source of random effect, which is review. Now I've given different letters to these different random effects just to show that they're different. So what's changed is we've added in an extra error term. We've worked with the model where we had a random intercept and slope for participants. Now we've got an extra random intercept for the different source of interdependence. A lot of output here. I'm showing you the grant model, the grant only model, participant only model, and the grant and participant model. I'm not going to go through everything that's different about these three. I'm just going to say, like, big picture, what's changed. So one thing that's changed is that in this model, we've got 4 different variances, basically, 4 different sources of error. We've got 2 sources of error for at the participant level, 1 source of error at the grant level, and 1 source of error that's not tied to any particular level. In the model to the left, the grant model, we've got 2 sources of error, grants and extra. And on the participant model, we've got 3 sources of error. So 2 for each participant and 1 leftover. So we basically add 1 extra source of error. We've taken those 4 parameters that we were estimating before and gotten them all from the same model. We consider the fixed effects. We have the same fixed effects. We're still have the fixed effects for the intercepts, the average score, and for the slope for quality. And it's a little bit hard to see up here, but even though the fixed effects are slightly different, in each case, they're very, very similar. Like I said, this is something that will generally be true. So they're a little bit different, but they're very, very similar. We consider our significance tests, the F, degrees of freedom, and p-value, the things that we're making inferences on. That's something that is quite different. So the p-value is around 0.01 here, it's 0.0005 here, and it's 0.009 here. So we found something that does differ even substantially across the models. So that ought to tell you that there's something that's happening under the hood that affects our inferences. There's something about accounting for the multiple sources of variation within the same model that affects whether we feel confident enough to claim that there is an effect for quality or not. That's something I'll describe in a little bit more detail on Wednesday. Again, I'm not going to go into like everything having to do with this model, but I'll give you some big picture ideas. And I'll especially go through some design choices that you can make, because that's the whole reason I wanted to talk about this in the first place, is that it can have a lot of influence on how you design your studies. And I think that's something you should know. So I'll see you all on Wednesday. Thanks a lot.
Thank you.